So without further ado, I'll introduce Dr. Joanne Blanton. Jo is currently Senior Lecturer and Digital Learning Leader at the Graduate School of Education at the University of Melbourne. She has a wealth of experience in Victorian schools, as you will have seen in the booking page. And I'm excited to hear more about the ideas Jo will be sharing today, which range from the use of robots and electronics for data gathering, right through to coding and using Scratch and other coding environments in the science classroom. So take it away, Jo. Thank you.
Okay, thanks, Nathan. Well, good afternoon, everybody. Well done. 48 hours for most of you until school holidays. Well done. What a strange term it's been. I'm going to start with an acknowledgement of country. And because we're remotely located and we don't know where everybody is, I'm going to offer a general acknowledgement. So we, as a group, acknowledge the traditional custodians of the land and waters of Australia and pay respect to all elders, those in the past, those working with us in the present, and we look forward to working with those that emerge in the future. So welcome today, and what we're going to be doing for the next hour is a little bit of playtime. So we know that from research, we know that when we get students working with new technologies, we know that we have to give them playtime. And I'm sure you've experienced it. For example, when you had an interactive whiteboard in your classroom for the first time, or a data projector, I'm sure you noticed that the first couple of lessons, it was pretty hard to do anything except have a focus on that. So we know it takes between 2 and 3 weeks to kind of get used to something. And as teachers, particularly in the current situation, finding time to play is really tricky. So I've built some time into the webinar today. We have an hour together. I'll finish 5 minutes early so that we can have questions. You will get a PDF copy of this presentation, and as Nathan mentioned, there'll be a recording as well. Please do comment in the chat, and if you want to interrupt, let's have a conversation, feel free to do that. Just message in the chat and then Nathan will let me know that I need to stop. As you've all experienced now, this way of teaching and learning is different. And so I want this to be more of a conversation, but we'll see how we go, because I know as teachers, as a teaching community, our brains are pretty full after this term that we've just had. So let's see how we go. So we are going to talk about coding and algorithmic thinking in secondary science education. And we do have some very strong expertise already in this group. So I'm hoping that they might jump in and offer their insights as well, Paula. And feel free to ask questions or write your own notes as we go through. It's always hard with these kind of technology webinars to target the learning specifically for everybody. So what I've tried to do in this session is provide some introductory information and then some more advanced activities as well. So the idea is that no matter where you are on your use of coding and algorithmic thinking in your science classrooms, you will leave today with some ideas for something new that might contribute and support the student learning in your classroom. A little bit about me very briefly. As Nathan mentioned, I am Senior Lecturer at the University of Melbourne. My background is in primary school education, but I've taught secondary school in France in a second language, in North America, and also I've worked in quite a few secondary schools here in Victoria as well. My background is from outdoor education. So I ran an outdoor education camp, a YMCA camp in America for nearly 10 years. And a lot of my work with technologies comes from my understanding of outdoor education and the ideas of active learning and constructing learning with others. So you'll probably see that come through. These are our 5 areas that we're going to look at today. So we're going to talk about why we're bothering. Because why we're bothering talking about technology, we know that we've all had to experience remote learning in the recent times, but what we're talking about here is different. So we're going to have a look at kind of the cultural context. And the reason I do that, it comes out of research that I've done that says when you look at the teachers that do use technology effectively across primary and secondary, what is it that helps them do that? And one of the things that helps us be more persistent, more resilient when we use technology is an understanding of how what we do is reflected in the world of work, the world at large beyond school. So we'll have a look at that, and we'll go through a few different things, and there'll be some time to play, brief time, but enough to open things on your web browser and hopefully bookmark them for later. So let's have a think about why we're leveraging technology. And you may have heard of Moore's law, which has been around for a long time. Now, these approximations here, these examples, come from the Microsoft website, and they are about 4 years old now. And we know that technology is changing exponentially. And so this is what we're trying to get across to both our students and our teachers, is that Moore predicted that technology will double in speed and halve in size every 18 months. And we know that that has happened. In fact, it's more than that. And there comes a point in which things can't halve in size anymore. If you think about mobile phones, the size of a Nokia phone, what it went down to, and now we're back up to the big iPhones, right? So there are limits to this. But if cars shrunk at the rate of transistors, they'd be the size of an ant today, just in the last 30 years. And I like the sound of this one. A flight from New Zealand to New York would be over by the time it takes to fasten your seatbelt if air travel increased at the same rate as technology. So technology is an outlier in our society for the rapidity of its change. We don't have anything to compare it to, not even when you look at things like the Renaissance and huge other technological experiences that previous generations have experienced. We don't have anything to compare it to. We know that things have changed quickly. We know that storage, everything. And one of the interesting research articles I read recently was talking about if coronavirus had happened 5 years ago, we would have been really, really stuck. Because just in 5 years, the video technology, bandwidth, and home technology use has increased so much in 5 years, it made remote learning in schools possible. So in 2001, so almost 20 years ago, this was the comment that Kurzweil, now Kurzweil is a futurist, he has like an 85% accuracy rating in his predictions. If you're ever interested in what's going to happen next, have a look. But he basically said that we've got a new century here, but we're not going to have 100 years of progress. It'll be more like 20,000 years of progress. So we have this exponential growth. And so technology in education and in science and STEM needs to take account for that. But of course, this paper was written in 2001. And already this is very out of date, and Kurzweil has even more specific predictions today. So we know things are changing. And the reason we talk about technology in things like science and maths and across humanities and everything is because the world has changed. The opportunities for adults in our societies has changed. And I used to kind of counter that comment by saying in first world countries, in developed countries. But the reality is that mobile technology has influenced globally now, as we've seen in places like India and Southeast Asia, and how they've managed to maintain their economies to a degree more than expected during the COVID. So this is a very quick example of why we're looking at technologies together, and it's called the door problem. So this is Liz England's blog. She is a game designer, and she has a fabulous blog that talks all about technologies and the types of thinking that we do in these roles and what needs to be taught in schools. So she always gets asked, what does a game designer do? So here's what she says. This is what a game designer does. You have to be able to answer all these questions, okay? And we're just saying, for the purposes of this example, that you are just making a door, one door in a game. You can see it up the top there. And these are all the questions that you need to be able to answer. Now, these are not arbitrary. All of these questions are connected to each other. All of them require problem-solving skills. They need systems thinking in order to make so that the virtual world makes sense. And they need an understanding of how technology works in order to be able to answer them. Okay, so if you have no sense of how technology works, you won't be able to talk effectively to things like this. Do doors lock afterwards? What does that look like? What are the norms in that space? You've got more questions. Okay, so far we can see that just in this one industry, which is a massive burgeoning industry around the world, we can see that there are a huge number of thinking skills involved. And if our students have never had experience of that kind of thinking, this is an opportunity that might be lost. Of course, not all our students are going to be game designers, but it gives you an example of one industry. But then it is not just about the individual person. These are the jobs that now exist in game design that, that your students will need to be aware of, even if it's not in game design. So something like a sound designer now has much wider applications than working at a concert. A sound designer can work in any industry that has blogs, that has video content, that has audio on their website or in their virtual presence. So all of these people are now required to have these thinking skills and to interact with this one new role of game designer. And it keeps going on. So you can be a lawyer, but if you go off to be a lawyer, you still need to have an understanding of the types of thinking that go into the world of technology and the workplace today. You might be, you can see there are programmers, but it's not all programmers. We've got a character artist. I don't really care about this door until it can start wearing hats. Well, okay. We have monetization designers. So that is an economist role that just didn't exist 15 years ago. We've got quality assurance tester, which is what I think my son would be interested in, running and jumping and basically trying to break the game. Okay, and you can earn quite a lot of money doing that. And it keeps going and keeps going. And then, of course, the player doesn't even notice the door, but this is the amount of work that's gone into it, the type of thinking that is now required. Another reason we look at technology in the science classroom is that we have an increase in the number of internet devices, and it'll be even bigger. This is the 2016 Bureau of Statistics, the census. But here you can see, and this is an interesting trend that's come from the previous survey as well, is that the younger your children, the more devices you're likely to have. So if your children are under 15, you're more likely to have more devices. And the another interesting thing was that the ownership of these internet-connected devices was not different between major cities, regional areas, and remote areas. So although we still have technology and internet access problems, the devices are actually there. So we need to leverage these. So I'll just stop briefly. And did we have anything in the chat?
Just a comment from Paula regarding the link to systems thinking there, and that's one of those areas we sometimes talk a bit about it as a neglected area of the Digitech curriculum, that systems thinking skill. And I think that team of people working on the door is a great example of how they all have to work together and how it has to fit together. So, yeah.
Yeah, thank you, Paula, that's right. And I think systems thinking is something that has really been previously relegated to things like leadership and manufacturing. So they have quite a strong presence in the research around systems thinking, but really we need our students to be thinking about it. So let's keep moving. And you've probably seen this, and Paula probably worked on this, but this is just to make sure that we're talking about the same thing, because terminology in this area can be a bit challenging. So what we have is we have an ICT capability nationally, and we have a digital technologies learning area. And so the learning area has the same importance and weight as things like humanities and maths and science. And so it sits there. How it's taught in secondary schools is up to the school. Some schools have dedicated staff that do this. Others have a STEM approach, and you might have that in your class, in your school. And some places tie the design technologies and the digital technologies learning together. Whichever way it's presented in your school, there are key ideas that need to come through. And the reason we're looking at algorithmic thinking, or computational, we'll get to that in a moment, and science, is that there are some natural overlaps. In Victoria, we've taken the ICT general capability, and they're mainly embedded across these areas. They can be anywhere, but there is not a specific separate ICT general capability in the Victorian curriculum. So because this is a webinar, you could be working in other states that have different approaches, but this is just to confirm that this is the ICT capability, and these outcomes are embedded in other spaces. So everybody is responsible for the teaching of digital technologies. And as I said, it will come down to whether how your school decides to staff this area of learning. And for many of us, it means that we take on a number of the outcomes in our science classrooms. And it's a way of looking at science using technology to enhance science learning outcomes, but also giving a real world context for learning about our digital systems, processes, and creating digital solutions. Okay, and some of the terminology in the technology curriculum and the science curriculum overlap really strongly. So this is from the Victorian curriculum, and we have the digital technologies and science, and this is what it says. As I just mentioned, there are overlaps or complementary aspects between the two areas, and these key concepts are what we need to get students to take away from our experiences, from the learning they do with us. So not everything will be covered in every year level, in every unit of study, of course, but these are the key concepts. So it's worth thinking about how your school is presenting and evaluating the digital technologies domain learning area, and how that might work in your science classroom. You'll notice that a number of those key concepts are the same as science. So for example, implementation, interactions, data collection, data representation, data interpretation. If you think about a formal science report that we often have students write in secondary school, there is significant overlap there, okay? Any questions about that at the moment? I've got a couple of comments.
Yeah, no questions at this point.
Okay.
Yeah, I might put in a couple of links. I know that the list of concepts there looked like that was from the Australian Computing Academy, Joe, so I might give the link there, and I'll link people to the relevant pages on ACARA's Australian curriculum and also BCAR's digital one.
Yeah. And the Digital Technologies Hub is probably a good one. They're all at the end of this presentation as well.
Cool.
Yeah, check them in. And Paul has just given us a lovely update that ACARA has just begun reviewing the digital technologies as well as maths and the general capabilities. So we'll see, won't we, Paula, what kind of happens from here. But we can only work with what we've got at the moment. So let's get into thinking about these things. So this purple box here is taken from the Digital Technologies Hub. If you haven't seen it, you really should. It's going to be your first port of call for these resources in your science classroom. And you can see that here, the big circle is computational thinking. And computational thinking is described as the approach we draw on when thinking about how a computer can help us solve problems and create systems. So I want to highlight the word thinking. It is very much a thinking curriculum. There are a lot of activities. There are obviously clear outcomes that need to be addressed, but there are a lot of thinking skills involved in the digital technologies curriculum that you can apply to your science classroom. So I've just made the bubbles here to represent the key aspects of what we mean by computational thinking. It doesn't mean thinking like a computer, which is what I hear sometimes. It means thinking how a computer can help us. And we can only make those judgments if we have a strong understanding of how computers work in the first place. So we've got algorithmic thinking here with its clear links to maths. Even if you don't teach maths, algorithms will be a term you're familiar with. So we have all of these general ideas that go into computational thinking. And so we're going to have a bit of a think about this idea of algorithmic thinking as a major component of that today. But you can't really do computational thinking without all of these ideas coming together and linking together. So this is what an algorithm versus a program, okay? And this can be tricky. So one of the other challenges with language around this stuff is that computational thinking in America is often referred to as the same thing as algorithmic thinking. And they use algorithmic thinking to refer to computer work, and then they have other terminology for their maths. So just for us to be clear today, we're talking about a list of steps that you follow to finish a task. So think in your science classrooms about your prac lessons where they follow steps. Think about how they write up or how your students present their findings, how they make judgments about what has happened, okay? And the steps will lead them through that. Once we have all of those steps put together, we have something like a program that will work to achieve something specifically. So you've all used algorithms, and Google Maps is always, this is just my route home from work. Algorithms are everywhere. It's very hard to not have your life impacted by algorithms anymore, which is why algorithmic thinking is something that we as teachers need to really consider and reflect on. If you've ever used Google Maps and you see the red line that says, gee, the traffic's bad, that is not from satellites. Sometimes it's drawn from Vic Roads cameras, but mostly it's drawn from the people in the cars ahead of you who have Google Maps on their phone. And so their information is feeding back to create a pattern that is then analyzed through an algorithm to say, is this normal traffic? Is this heavier than usual? Is it not? So algorithms are everywhere, and algorithms are a list of steps. And there we have. So let's think about flowcharts. And I know in science we often use flowcharts to explain how things happen. This is the typical example that we use when talking about algorithmic thinking. How do you find the largest of the two numbers? And this is a useful one because it has a sequence, it has branching, and it has iteration. So you can go back on yourself and keep going round and round. So the branching and iteration is important. So whereas in a science experiment that we simply present to students, we might give them 4 steps to achieve. If we can think of that in an algorithmic or computational thinking approach, we can start to say, what if? And what if, and then what? And so that's where we start to get into those thinking skills in our science. All computer coding is based on the premise of if this, then that. If this happens, then do this. If this condition is met, then apply this algorithm, okay? So if this, then that. We have lots of different types of flowcharts, of course. These are text-based, but they can be image-based as well. So we've got Hey Jude with lots of branching and iteration. And then, of course, we have Scratch, which I'm sure a number of you have used before. What I wanted to highlight today with Scratch, though, is that we don't stop using Scratch at year 6 and then start jumping into other things straight away. Scratch was developed by MIT. It is a fully legitimate expandable coding approach, and in behind each of these blocks in the code there is real coding language. So when you go into Scratch, you can click on them and you can see the JavaScript coding language on the back. So we call this block coding or visual coding, and we're dragging things together. So in the previous flowchart, we saw iteration and branching. Well, here we're seeing branching. If this, then that. And we're seeing iteration. See the forever loop that goes around and around. So it's a different way of exploring those concepts. I just want to I want to highlight the resources that are on Scratch, because you don't have to start from scratch, from the beginning. You can use resources that have already been made. One of the wonderful things about using Scratch in the science classroom is that lots of other teachers have already done it. And so you can go in and you can use what someone's done and ask your students to prove or disprove. We know in teaching the strength of providing examples and non-examples for our learners. So in prep, we teach students what a triangle is by showing them triangles and rectangles and asking them to find the examples and non-examples. In the science space in secondary, we can take a similar approach. So we would look at these and we would say, does it make sense? Can you prove to me that these work? So let me have a look. So we have here, this is, and again, this link will be in there, but you can get to it through scratch.mit.edu. You can download Scratch to use it offline, and I know a number of schools do that because they don't want more accounts for their students, and they want also the students' work to be on their local device. So it's up to you how you manage that, or you can sign in and create classes within Scratch as well. You can see that all of these are about life sciences. So these are made by teachers and or students, a lot of cases through groups. And we can take any of them and we can, let's go into this one, and we can explore the scientific concepts that are here. Okay. The bonus of these is that we can see inside, and that means we can see the code. So I can see when I received blah, 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 when clicked, show blah, blah, blah. From here, our students can actually build from. So it's a bit of a mashup. So they can take what's already been created, correct it, improve it, reduce it to its simplest parts. So we need to think about the type of learning that this coding offers, which is exploring examples and non-examples. And it also gives us a way in to these ideas of algorithmic thinking, because they're demonstrating scientific concepts through algorithmic thinking. Coding is inherently systems-based because it is logically sequenced. And so systems thinking comes in here as well. Let's go back. Hour of code. Now, if you are just starting to think about algorithmic thinking and coding in your science classroom, this is the place for you. So you need to have a look at code.org. You can see it's got famous people. It is American-based, but it is a charity. It has non-profit status, which means that it doesn't have a specific bias towards any particular politics. And it is more open source. One of the exciting things about Hour of Code is that it is constantly updated. It's also moderated by large amounts of teachers around the world. So if anything doesn't work, or it's inappropriate, or it doesn't match, or it's not the right for the age group, it can actually be changed. Oh, apologies. One of the things we love about code.org is that it is encouraging more diversity in algorithmic thinking, coding, and programming. And as we saw at the beginning of our webinar, offering those opportunities to our students means that we open up many, many doors for them. So even if they want to go into, they want to be a professional artist, or they want to be a dancer, or they want to be anything in the world, a gardener, an engineer, any of these professions these days require an understanding of how these things work. So we know that more girls tried computer science just in code.org than in the last 70 years. And that's based on enrollment in computer science in America and in tertiary education programs. We also know that working in these kind of online like code.org is addressing diversity, so that we're increasing diversity. And one of the important things about using technology is that we are expanding the diverse nature of what is offered, so that we don't have products developed for only a certain section of society. We don't have scientists who only explore and understand science from their perspective. We're trying to broaden that understanding. I'm going to open up a couple of windows. So if you sign up, it's a free account. There are a number of things you can engage in. The teacher community is really useful. You can type in questions and they will get answered. The professional learning is, a number of it is free and online, but a lot of it's paid. So you might want to have a think about that. But the course catalog is exciting. You can go in here and you can match your level of learning and your students' level of learning to a range of different programs that they have built in. One thing that I've seen used really well in science in secondary is the app lab. So you can now build fully functional web apps, which you can use on your phone. It's basically just accessing a website on your phone. But students can build them in Scratch using the same Scratch language. So for example, our secondary school earlier in the year, much earlier before we were remote learning, they were having their students work in groups of 5 in their Year 9 science class, and they were creating an app to explain why one part of the school indoors was much warmer than the other. So when we had the heat of the summer and all the students were crowding at the fun end of the school, they wanted to know why it was so much warmer. And so they created an app that actually had a map of the school, and you could click and record readings and then analyze the data. So App Lab is a really great place to start. If code.org has 1 hour classes, because I'm logged in, it's not going to show me the right thing. It has 1 hour. You can learn to code in 1 hour. So if your students have never coded and you want them to engage with those ideas that we looked at in Scratch, in any of these, then code.org is a way to go. And as Nathan has mentioned there, you can also use it. You can use App Lab with JavaScript as well. So we can move them on from visual coding if that's where they're starting, and we can move into text-based coding. All right. We won't have a look at that. So a couple of examples of things that have been built for science classrooms is building a catapult. So if we want to have students understand things like motion and forces, or the white blood cell, or gravitation, we can use the ready-made versions of these, and then perhaps they create their own, they modify, and so all these things are freely available and really useful as simulations for a science classroom. And I know many of you will be using simulations in your classroom. The difference with these is that they are editable. Your students can change what happens. The catapult was not in App Lab. That is just a Scratch code that you can get from this link down the bottom here. That one's on Hour of Code. Someone just popped up and asked. So you can get the catapult, and you can change in the catapult. You can change the range, the air pressure, humidity, all of that kind of stuff, so that we can get students really engaged in some of that data that they can collect. This one is Chemistry Maker, and again, it's already been made. So for some students, sorry, my mouse is not very helpful today. Let's see if that will open. Yep. So in Chemistry Maker, we actually have to have them build atoms with molecules. And so if we're trying to get them to understand what happens here. So in Year 7, this is probably all you need to do. In years 9, 10, perhaps even into 11, I'd be asking the students, okay, if we take out the carbon atom, or if we take out the ability to add O2, what could we add in and still have fully functioning chemicals here? And the bonus, of course, with these is that we can see inside right away. Okay, so here is that code. So we don't have to start from scratch. We can build from here. Instead of writing a lab report or an essay on how, on the structure of water and how it functions and the bonds between molecules, we could be asking them to provide us with a screenshot of their code or the link to their interactive so that we can actually measure their learning that way. All right, questions. I've got a few comments up here. Oh, Nathan's put a few links. And Nicola's all good now. Anything anybody wanted to add?
I was it's going back a little bit, but I was a bit guilty of that poorer definition for computational thinking that you mentioned earlier, thinking how a computer thinks. Although I think it's necessary to still do it. It's not the whole definition. I heard a good one recently where it's approaching a problem so as to be able to design a solution in such a way that a computer can do it, can carry it out. And that's kind of, a useful definition that I've heard. Yeah,
that's good. I like that. Yeah, and it's, there's no right or wrong. It's just that we have to be clear about the definitions we're using when we're talking to students and talking to our colleagues so that we're all on the same page. And then Thomas, what's Thomas's question there, Nathan?
So in some schools, they use an offline version of Scratch where it gets installed on a local machine. So it's difficult perhaps for them to get some of those programs that are available on the community. I'm not sure, can you bring them in an easy way?
Yeah, it depends on the permissions that the creator has set. But if they've enabled it, you can just download the file and then you open it on the local version of Scratch.
Yeah.
The other thing you don't get with the local version, and if you're talking about the department image that's on school computers, it doesn't get updated as much as the online version. So as they add more blocks and refine the coding in Scratch Online, you don't get that as often. But for most situations, it's not that big a problem.
I found it interesting too that there's sort of different iterations of Scratch in places. Like there's one that's connected to a website called Machine Learning for Kids, and it has speech recognition in it, whereas the regular Scratch doesn't. So it's funny, you can find different sort of versions of Scratch that have different features and different blocks.
And Thomas has posted asking about communities of practice. Yes, you can still develop communities of practice around the coding and the work, but you'd have to do it in an iterative way rather than a combined collaborative way. You'd have to have groups of students making and designing and then asking for feedback and developing the community of practice in a much more structured way than the more free-flowing conversational shared development that is available in the online space.
I was just going to, before you go on, Joe, in terms of students going inside the code for, say, a Scratch activity that you're doing in science, if you were working in a school, say, where digital technologies is a distinct subject, would it make sense to kind of cover the basics of Scratch in digital technologies so that students can then come to science and be familiar with it when it comes to looking at those programs?
Yeah, it goes back to Thomas's communities of practice. What we want to see is schools where teachers work together on this kind of thing. So just as we're all responsible for literacy and maths, no matter what we teach in secondary, we're also asking people to start thinking about digital technologies in the same way. It's a shared responsibility. So yes, it would be good if there are other areas. So the idea of algorithmic thinking is obviously an outcome in maths learning as well. So you want teachers, hopefully, to be moving beyond their discipline area, which is not the traditional approach in secondary schools in Australia, or many other places, to be honest. We tend to have our subject that we teach in secondary. So these kind of activities can be really rich. And if you think they're too big and too in-depth for your 2 hours a week with your year 8s, then think about speaking to things like the library staff and any of the STEM other areas. Even literacy, your English teachers can provide ways of thinking about explanations, engaging with different media.
Terrific. Thanks, Joe. I'll let you carry on.
Okay. Okay, just checking that was all right. We're back here. All right, let's look at some robots. And robots are not just for little kids, although they have some very cute little robots for early childhood and primary all the way up to year 6. But we can use robots in a number of different ways to focus on algorithmic and computational thinking in the classroom. So here we just have a range of robots that are codable. Not all robots are codable. Some robots perform more like a remote-controlled car that perhaps you had as a child. And some of them have the ability to input code directly into the physical device by pushing buttons on top. So B-bots, if you've seen those little bumblebee-shaped robots. And others are connected via Bluetooth. And then all the way up to things like Lego Mindstorm and all those new Lego robots that actually require a physical USB connection to a computer because of the complexity. So where do robots fit in science? Well, they fit in, and these are not from a specific level, they're the generic inquiry skills and science understanding skills. And I've just given you a couple of examples that would match these activities that you see in the images above. So we can see that the center image is a sphero that has been turned into a chariot, and it had to be a chariot that was moved easily through the air, limited friction, all of those kind of science ideas. So we're talking about, we're back to that idea that science is a thinking curriculum, and also digital technologies has a lot of thinking ideas in it as well. And so these kind of activities are where they overlap. We need students to think about the problems and the systems involved. You can see the systems that are in place here. For this example, the sphero had to be able to pull a certain weight. And so they had to move a certain weight. So it could have been, I apologize, it could have been that those rocks were on top of sphero, behind sphero, or in front of sphero. And yet they've worked out a system that places the forces of motion in a correct sequence to achieve their outcome. We've got the idea of measures and control variables that are appearing in this use of these robots here. And we've got the idea of collaboration and planning. So 3 different areas from the science curriculum that connect really well to the use of robots. In secondary school, and these are always changing, they're changing very quickly. These are science-focused robots, I guess you could say. The Edison Robot, the orange one, has a lot more functionality than your basic robots, in that it enables you to use things like infrared sensors, light sensors, sound reactions. It can record movements, and it can do a huge amount of things through programming. So if you were looking for robotics in your schools, these would be the ones that I would suggest you start with, because they are expandable. So you might have seen the Dash robot that is blue, turquoisey blue, and it looks pretty much identical to this guy here. The black version, he is designed with more sensors, different motors, the ability to track movement, and it has a better sense of proprioception. So its sense of itself in space is actually there. So we can do a lot of scenario-based learning in science with this. So for example, through the bushfires at the end of last year, a year 9 science teacher I know was working with these robots, the Black Wonder robots here, and asking them to create a situation in which a robot could be helpful during bushfire season. And so they created scenarios of, how do you get it to go up and over? How do you know, how does it know when to speed up so that it can get up and over that broken door that's lying down, and all of those kind of things. And then the science we pull out of the sensors becomes part of the science learning in the classroom. One of the things that we don't do as much as we probably could is the idea that robots are a way of generating data in our science classroom. So we can use things, and this is just a sphero. These are year 6 students, they're a bit younger, but we can use robots to generate data. And as you remember from earlier in the webinar, there are specific outcomes in science that focus on data generation, data analysis and data representation. And so using things like Sphero or any of those robots we've looked at, you will gain data back when your code is enacted. And that data can be used to explore things like the scientific process and going through an inquiry phase, through understanding, making sense, expanding, going further, and those kind of ideas. So I really want to suggest to you that robots are not just about achieving a particular goal or enacting a scenario, but also can generate real life data that can be useful for students. All right, anything about robots before we head on? Nathan?
Oh, no real questions. A couple of comments. Paul made a comment, there's strong connections between the inquiry skills in the science curriculum and the ways of thinking, or the thinking skills in the Digitech curriculum. And it's a good thing if you can identify some of those commonalities. I was going to make the point too, with robots like Sphero, and also you can do a lot these days with the microbit by adding it to other things. But there are ways, it's not always straightforward, but there's almost always ways of exporting that data, getting it into a spreadsheet, and then you've got your whole data representation, and you're working with data as well. Because sometimes we get stuck in that, we'll gather data by observation, we'll count the cars in the car park, or we'll get it by doing a survey, but you can also get it directly from robots and things like that as well.
Yeah, one of the interesting things I saw robots used for in science last year was the secondary school, and they had they were using the portable classrooms. They're often raised up, and so there's a space underneath. And they thought they had a rat problem, and so they worked with the maintenance staff and actually wrote a code for the Mindstorm, and wrote the code to send the robot underneath, take a series of pictures so that they made sure they got a 360 degree. They took temperature readings to find out if there was warm bodies down there. And then they brought that data out. They created a map from the data, and then they pinpointed where the rat control pellets should be.
Oh, wow, terrific.
There, yeah. So collecting the data and then using it as a problem-solving approach, really exciting, and the kids were so excited.
I think it's great too if you can bring in that tangibility of the robot as well. Like I remember somebody told me about one where they used it. They made, I think they used a Mindstorms, but it was one that you could build from, and they had it like dipping into a tank. Every so often they coded it to dip in and measure the pH level or the temperature of the water and things like that. So that physicality, I think, is really good.
Yeah, and some of those things that we can't do in a traditional classroom. So engaging virtually with spaces is when a couple of years ago, when the California bushfires, was it last year, were really bad, there was a story on the news about dogs, and how there was a special section of the rescue, 000 people who were going around and checking every house for left behind pets. And so in this year 8 class, the students in groups created a plan. They were given a map of a particular area. It was only small, like a 500 meters square, but a real life map from Google Earth. And then they created a way for a Sphero to go around and actually check all of the things. And so they had to look into biological science around what would be the signs of an animal being there. If it's a bird, how is that different to detecting it than a dog? So we could have it sound triggered by a bark, but how will we make the dog bark? Well, we might need to ram into the door 3 times and those kind of things. So, and they couldn't obviously enact it, but it was a way to work with the students around those systematic problem solving theories, which is really interesting. All right, I'm just noticing the time, so we will just have a look at the idea of chatbots and artificial intelligence as an approach to coding in your science classroom. Now, if you're not sure what I mean by chatbot, it is that little box that appears on websites that says, "Hi, I'm here to help. What would you like to know today?" And the one I've used the most is on the Telstra website, although they've taken it away during COVID. But there is, while you might think you're talking to an actual employee, the majority of chatbots are automated, artificial intelligence, up to a point. So we're still looking, we're still developing the idea of natural language recognition through chatbots, but we can do, as teachers, a lot of cool stuff with chatbots as an artificial intelligence in science. So this is an area that is just taking off. Bill and Melinda Gates are giving $240 million just for one project that personalizes learning through artificial intelligence and machine learning. So we are taking chatbots as our example here. So let me have a look. Apologies. Here we go. Okay, so here is an example. Snatchbot is a really good place to start. You can build these, or you can have your students build them. Usually we do the see one, do one, make one kind of approach, but it depends on your context and your students. You can use chatbots to reinforce concepts. You can use them to find out where the pain points are for students. So in a particular understanding of a chemical process or a biological concept, where is the difficulty? And the chatbot can help you understand that. So here's an example of one. We're just going to reply yes, because he says we're excited. Exciting, yes, it's because I just reloaded the page. I knew you'd be. So these are obviously set responses. This is not fully natural language. Okay, but you can see that I can anticipate what most of them say. How about having a pizza class? Let's order it and how to add. If I say okay, what's he going to say? Tell me how many pupils. Everyone can see this okay, yes? Yeah. How many pupils? Count attentively. I know exactly in our school we can have up to 10 per class. There's definitely no.
We might just want to zoom it in just a tad, Jo, if you can. It's just a little bit small. You might want to zoom it in just a tad. It's a little bit small.
Good, thank you. That's helpful. That's a bit bigger. Yeah. Okay, so this is a chatbot. It's a sample one. It's going to lead me through a maths problem. And so when we think about things like remote learning, where we can't be physically right at the student's elbow all the time, chatbots can be something that we can prepare in advance. Now, the challenge, of course, is understanding how chatbots work. And when I show you, this is a chatbot I've made and I use quite often in one of my master's courses. And this is how it looks, and you'll notice it's a flowchart. It has iteration and it has a lot of branching. And so we are thinking about how do we represent the questions our students have, or the concepts and the connections between concepts, using things like chatbots. So this one was around the concept of clinical teaching, which is a concept we use as a pedagogical approach at MGSE. And you can see that I have pre-prepared the responses they can choose from. So they click on it. If you say yes, that's great. You've heard of it, but do you know enough? Is it just heard of it? No, thanks. Okay, then you can just stop here. Or we can say, yep. If you want to learn more, yep, you're a lifelong learner, and it will take them back to the options which are down here. So there's a way of creating these. You can see it's a very visual approach to coding. It brings in all of the systems thinking, algorithmic thinking, computational thinking ideas. There's even abstraction and decomposition in this, which are the other two major concepts in digital technologies. In that, in order to create these, your students have to say, what are the alternatives? So we're back to examples and non-examples. What might they say? What might be the responses? And I have to find the right one. Apologies. Yeah, here. So if you took something like this scientific concept of how the chemical process of a, whatever that is, can't remember what it's called, heat exchange. If you provided this to your students and asked them to create a chatbot to explain it to other people, there is a lot of learning involved in that, because this at the moment is fairly sequential. But what we're asking the students to do is to think, what are the steps? What are the potential misconceptions? And how might we present them so that the other students follow through the correct aspect. So if you have a question that says, okay, the reactor's up and going, shall we connect it to the heat exchanger or the distillation column? And the branching will say, if they click distillation column, it'll say, no, sorry, not yet. We haven't actually built the full heat exchanger. So let's have a look through. And so we are using the flowchart idea, but in a slightly different way. Let me just go back to here, in a branching way. So this is, although it's not actual coding, it has a lot of the same thinking skills behind it as coding. All right, so I'm just going to finish up and then we'll have a couple of minutes for questions. In some research I did with a large number of primary schools a couple of years ago, this is a summary of a few different teachers, quite a few teachers, who said, why are we teaching technology? And this is what they said. They said it's the 21st century, it's equal to maths and electricity, ICT. That they feel like their students need to have, they have a right to understanding maths, and they have a right to access to electricity, which is also part of the United Nations rights program too. And ICT is up there with that. So that's just teachers are positioning it. This is what's happening, and this is your 60 seconds, an internet minute last year and this year, and this was earlier this year. So of course this will have shifted again because of COVID and what's happening. But this is the space that your students are engaged in. This is where their time goes. This is where their social lives occur and where their social interactions are built, and their relationships often occur as well. Seymour Papert, he's kind of the father of computing. In 1980, he talks about technology needs to offer low floors and high ceilings. And what that means is that everybody should be able to enter with low floors. So when you think about technology in your classroom, but there should be really high ceilings, because it should be able, students should be able to take their understanding to the next level and the next level and the next level. And when we're thinking about digital technologies in this space, what we mean here is if we just teach science concepts using pen and paper, we've given them a low floor, but where's the high ceiling? We have to think about what digital technologies add into our classroom. This guy, just to finish, this guy is not coming for your jobs anytime soon. Technology is built by humans, of course, and teachers will always be necessary. It's about how we as teachers engage with the technology to make sense of learning for our students. We are still the only ones who can do that. And then this is my favorite quote: there's nothing magical about any technology tool, because the magic is in the minds and hearts of teachers using tools to introduce students to new individuals, ideas, and opportunities. And hopefully today, there's some links, hopefully today I've given you some ideas for how you might engage in those new ideas and opportunities, and perhaps with some new individuals. So I'm going to stop there. Nathan, what do we have? Do we have any questions? And someone just asked for the catapult thing, so we'll go back to that.
Yeah, probably just need, it was after the link there. Yeah, just on the last section on chatbots, we have mentioned chatbots in a couple of our recent webinars actually this term, and I'll put a couple of links in the chat window, but we saw how they are connected with literacy in terms of interactive fiction, and you can even do that with speech recognition if you use a platform like Pencil Code. So I'll put a link for that. I'll also put a link for a colleague, Sanyan Dedic, created a learning sequence with videos going through using natural language processing to make a chatbot in Python, and it's got some sentiment analysis, which is great. It tries to work out whether you're being objective and whether you're being that sort of stuff.
Yeah.
So it's great stuff. So I'll put the links for those two in the chat as well. Were there any other questions from anyone? Because we've sort of reached the official end of the webinar, but if you do have, if you do have any other questions, please feel free.
So it's Kev here, Joe. I'm the manager of DLTV, but just wanted to formally thank you, Joe. excellent, excellent webinar. Really enjoyed it. I learned a lot, which is great. And Paula, thank you for all your comments. That was great. Really appreciate it.
Yeah, very helpful.
Yeah.
Yeah.
I just saw a question there from Thomas. You mentioned play at the start of the talk today. I was wondering whether and how creative coding might figure in the STEM classroom.
Yeah, so play as an approach to inquiry and personalized learning. So I guess I wanted you to have a play today, although we've just run out of time, but we've had some good conversations, so I think that's that was important. What we talk about with play is creative expression with technology. That's what we're looking for. We're trying to get students to use those more complex and connected thinking skills in ways that encourage creativity. And when you look at the overview of technologies curriculum, so the big word technologies with design and then digital underneath it, where it actually talks about creative problem solving in both those areas. So creativity as a form, as experienced by students through play, so that we can explore coding that already exists, we can play, manipulate, and we can create from that, and we learn through the doing.
Yeah, I as I said before, I think it's great to also get students out of the mindset that connects coding just with maths. Sometimes students are only exposed to coding in its connection with maths, which is fine. I mean, maths, there's a lot you can do to connect coding and maths, but literacy, other areas too, obviously science, there's lots of, and I saw someone mention that they're a music teacher earlier on as well. There's great ways to connect coding with music as well out there. So yeah.
Yeah, I used to teach, I'm a bilingual teacher by background, so taught in French a couple of different places. And we know that music and languages are, music and French, for example, are both separate languages. Coding is another language that sits alongside that. And so there are massive amounts of connections that we can make between how we understand music and language and coding as well, which is, it's really exciting. There's lots of interesting projects coming out.